224 maybe somewhere here. 8,000, where's my 8,000? So this is 14.7 DSIA, 50, 100. 8,000 is that line. That is 8,000. So at 8,000 and 224, so we may have something about 230. That number is 230 that the textbook said, right? 230. Of course, you will have to spend more time to find out how many pounds of water that will be in it. So this chart tells us amount of water, okay, wet gas, and it's reported as wet gas. So pound of water per million standard cubic foot. And okay, I look closer. 224, it is somewhere between these two numbers. In the middle, maybe, so what's this? Maybe closer to this one. And I have to do what? 8,000. So I keep going to 8,000. This is the line for 8,000. Yes, that's the 8,000. We go read over here. And they say, okay, 230. Okay. Difficult to read. And so when you do the exam, if your number match identically to the person sit next to you, please give me some down, okay? To not match. So we do the same for 4,065. 4,000, where's my 4,000? 4,000 is that line. 65 is maybe there. 4,065, I get, they said 10, so I should get 10. I should get something over there. It's even outside the range, okay? So basically we read this graph and find out how much water dissolved. Then we know that, okay, the condensed water is 220 pounds per million standard cubic foot. I better just give you that number, right? So you just get it, don't have to calculate. So I just tell you how many pounds of water per million standard cubic foot. From hydrate formation curve, next slide. At 4,000 psit, hydrate form at 74. Okay. 4,000 psit. Oh, there are many lines. What is our gas specific gravity? 0.6, right? That's the one, 0.6. So 0.6 is that one. And 4,000 is over there. So 0.6 and 4,000, I can read. That's the hydrate formation temperature, 74. So this one is easier to read. So we know that at 4,000, hydrate will form at the temperature of 74. That is 74, right? And actual inlet temperature is lower than 74. So we will have hydrate if we don't do anything. So we have to do something. Okay? Therefore, the formation temperature has to be reduced from 74 to 65. So delta T is 9. This tells us the minimum amount of inhibitor that we should add. I put 9 over there. Okay. I know the molecular weight of methanol. Molecular weight is 32. Right? K value is 2335. I put it in Hammerschmidt equation. 2335 and 32. 32. What I don't know is W. I calculated, I get W equal 11. So this means we have to add methanol until the methanol weight concentration or weight percent is 11%. So the amount of methanol, how much do we add? So 0.11 multiplied by amount of water, which is 220. So we had to add 24 pounds per million standard cubic foot. 24 pounds of methanol. Okay? 24 pounds of methanol. So that is the methanol that should go into water phase. Right? But some water some methanol will go into gas phase. How much? So I use another chart. This is the same chart that I put it here. Okay, the same chart. I just rotate it. So I have 4,065. How much is vapor phase? So I look at 4,000. 4,000 is outside the range, okay? 4,000 psi. I don't know where it is. Just extrapolate and try to get the same number that the text give you. And another one is 65. 65 is over there. So I say, okay, the ratio is 1. Okay, very bad, right? So 1 is the ratio between power of methanol in a gas phase per million standard cubic foot divided by percent in water. Then I go back. Methanol in vapor state equal to 1 multiplied by 11 equal to 11 pounds. So that will be amount of methanol in vapor phase. And this is a unit conversion, okay? 1,000 kilogram per cubic meter equal to 350 pound per barrel equal to that much per gallon. For oil specific gravity of 0.86, this is the specific gravity of oil that is given, right? We have about, multiply them together, we have about 300 pounds per barrel. So 0.86 multiplied by 350, we get about 300 barrel. So we assume that 0.5% dissolved in oil. That's the assumption, right? So then the amount of methanol in oil will be 0.5 over 100 multiplied by 300 pounds per barrel multiplied by 60 barrel per MMSCF. The number of 60 is the given number, so we say, yes, oil flow rate is 60 barrel per MMSCF. So this means we have 90 pounds per barrel MMSCF. That is the amount of methanol that will be in oil. The amount of methanol of 11, that thing will be in gas. So we have to add 24, come from Hammerschmidt equation, right? Plus 11, let's stay in gas phase, plus 90, that will be in oil phase. Add them together, 125 pounds per MMSCF. How much is 125 pounds? So 125 pounds divided by, do the sum unit conversion from mass to gallon, we need 18 gallon per MMSCF. Okay, 18 gallon. 18. You use 1 gallon milk at home, right? You have 18 of that or something. It's quite a lot. Okay. If you produce this 1 million standard cubic foot, if you produce more, then we will need more. Okay. There's a better chart in the back. We should use this one. And we will, it's 12:18. Okay, I still have some time. So this chart is from Surface Production Operation, 3rd edition. The previous one is from 2nd edition. Try to use this one because it has the number, okay? And the number is different. So 65 and 4,000, how much will be in gas? So this is a ratio of methanol vapor composition to methanol liquid composition. So we try to find out. We have 4,000 psi G, psi G and psi A, they are close, right? And we have 65 F, how come that's 80? 85, 50, 65, maybe somewhere there. So we have about 1.3, okay? The ratio will be about 1.3. Early on we get just 1, but this one tells us 1.3. So, I get 1.52 as my...
65 is a little closer to 5.
This one 65? Okay, I will have to check again because it looked odd to me. You see 25, 30, 35, 40, 45, 50, 55, and then it has 80, and then is that 65? I don't know. So Basically, with this graph, and then we can get that number 1.52. Do a little bit of calculation and we get another value. We do this one more time, okay, and put it in the homework maybe. Bye bye.